Today, we're talking all about electromagnetic shielding. In other words, how do you block the invisible forces that are all around us? So, let me ask you a question. What could your Wi-Fi router, your car radio, and your microwave oven possibly have in common? I mean, they do totally different things, right? One connects you to the internet, the other heats up last night's dinner, but they're all built on the exact same physical principle. And there it is. They all use invisible electromagnetic waves to move energy or information through the air. But what does that actually mean? What are these waves? Well, here's how we're going to break it all down. First, we'll cover the basics of these invisible forces. Then we'll get to know a device that creates them, the dipole antenna. After that, we'll dig into the really crucial concept of near field versus far field, which will lead us straight to the shielding strategy itself. And we'll wrap up with a fascinating little quirk called the skin effect. Okay, let's jump right in. Time to get a handle on the basics of these waves that are literally everywhere. So every single electromagnetic wave is made of two parts. You've got an electric field and you've got a magnetic field. But here's the key thing to remember. They are not always equal partners. Especially when you're really close to the source, one of those fields can be way more powerful than the other. You know, this stuff can sound a little abstract, so let's make it real. We're going to use a case study to see how all this works in practice. So meet the star of our show, a simple dipole antenna. This little guy is a total workhorse. You find them in all sorts of radio technology, and its entire job is to turn an electrical signal into an electromagnetic wave that shoots out into the air. And this is what that looks like. You're seeing the electric field radiating away from that antenna. That super intense red area in the middle is where the field is strongest, and you can see it spreading out in waves, just like ripples in a pond. Okay, to really dig into this, we're going to measure the strength of both the electric and magnetic fields as they travel away from the antenna, right along that straight blue line you see there. And trust me, the data this gives us is pretty fascinating. And that brings us right to the absolute core of this whole thing, the critical difference between the near field and the far field. You're about to see why a few millimeters can completely change the physics of what's going on. Okay, here's our first measurement. This graph shows the strength of the electric field, we call it the E field, as we move away from the antenna. And just look at that curve. It starts off incredibly high, but within just a few dozen millimeters, it just falls off a cliff. It drops off like crazy. Now, let's look at the magnetic field, or the H field. It also drops off with distance, which makes sense. But notice the shape of the curve. It's different. It starts lower, and it decays in a totally different way. It is not just a copy of the E field. So here it is. This is the crucial point when we put them both on the same graph. The red line, the electric field, starts out immensely stronger than the green magnetic field. Right near the source, they are completely out of balance. This changing relationship is, well, it's everything. And this relationship has a name, of course. It's called wave impedance. It sounds technical, but it's actually a super simple idea. You just take the strength of the E field at a certain point and divide it by the strength of the H field at that exact same spot. It's just a ratio that tells you which field is dominant. And if you graph that ratio, you get this. This is the wave impedance as we move away from our antenna. Right up close, it's a massive number because that E field is so dominant. But as we move farther out, it drops, and then something really cool happens. It just stabilizes. It flattens out into a straight line. And what does it stabilize at? 377 ohms. That is not a random number. That is a fundamental constant of the universe. It's called the impedance of free space, and it's the point where the electric and magnetic fields finally achieve a perfect, stable balance. And that right there brilliantly explains the difference we've been building up to. The near field is that chaotic region right up close to the source, where the impedance is all over the place and one field is clearly the boss. The far field is where things have settled down, the wave is fully formed, and that ratio is locked in at that constant 377 ohms. Okay, so now that we've got the physics down, let's bring it back to the real world. How do you actually use this information to block these invisible forces? This is the big question, right? Why does any of this matter? Who cares if a field is near or far, or if the impedance is 10,000 or 377? Well, it matters because you can't use the same tool for every job. If you want to build an effective shield to block electromagnetic interference, your strategy has to be completely different depending on which field is your main problem. Here's the playbook. To block a dominant electric field, all you really need is a simple conductive barrier. Easy enough. But for a magnetic field, that's not going to work at all. You need a special material with high magnetic permeability, which is just a fancy way of saying it's really, really good at attracting magnetic fields. It acts like a detour, pulling in those magnetic field lines and redirecting them safely around whatever you're trying to protect. You know, this dance between electric and magnetic fields has other strange consequences too. For our last section, let's look at one of the most interesting ones, a phenomenon called the skin effect. So check this out. When you send an alternating current through a wire, it creates its own swirling magnetic fields inside the metal itself. These internal fields create a kind of electrical pushback that's strongest right in the very center of the wire. And this pressure literally shoves the flowing electrons away from the center and forces them to travel along the outer surface. So the current ends up flowing almost entirely in the outer skin of the wire. And this leaves us with one last big thought. If current can't even use the whole inside of a wire at high frequencies, what does that mean? Well, it means engineers have to rethink everything. It changes how we design giant power lines for the grid, how we design high-speed data cables, and even how we design the tiny little circuits inside your phone, all because of these invisible forces and the weird ways they behave.